Well, this is an explanation for problem number 1 and the practice test number 2. So when we look at this example, we have a cylindrical can, radius 10 meters. Make sure you are underlining the facts as you do every FRQ. The can is initially empty, so at time 0, the height is 0. And we're going to enter the can during a 60-day period, so between 0 to 60. Now the height of the water is modeled by the function s. So s will be the height, okay? Important to remember. Where s of t is measured in millimeters and t is measured in days, okay? And then we're given the rate at which the water is rising in the can. So this would be millimeters per day. Okay, now that we've looked at the facts, let's start answering the questions. So for part A, what is the height of the water in the can at the end of the 60-day? Well, I'm given the rate of change of height, and I know that when I take an integral of a rate of change, I will get the actual height. So it will give me the actual value. And so I'm going to go from 0 to 60, and then I just use my calculator, and I plug the function to my calculator, and I would get 171.813. Now remember, it's always 3 decimal places. If you don't use 3 decimal places in the calculator, then you will be marked wrong. And so what does that tell us then? It's the height of the water. So then always, if you're given units, you say your answer in units. So it's millimeters. Okay, part B. According to the model, what is the average rate of change? Ooh, average rate of change. Well, since I'm given the rate function, then that means I need to find the average value of this rate function. And we know average value to be the integral from 0 to 60 of my function all over the interval, which would be 60. Well, we already found the value for the numerator, which was 171.813 divided by 60. And again, write your answer in 2 decimal places. So you should get 2.863. Now, what does that mean? It's the average rate of change in height of water. So that means on average, my height in water is rising 2.863 millimeters per day. Okay, great. Now let's go on to part C. I need to give myself a little more space here, so I'm going to erase the current work, okay? Okay, so part C says, assuming no evaporation, at what rate is the volume of water in a can changing? Well, volume of water in this can, what would be volume in this can? We were told it's a cylinder. So if we have a cylinder, we have something that looks roughly like this, right? And we know then we have to take the area of the base multiplied by its height. Well, the area of the base would be pi r squared times height. Now we want to find the rate of change. So really, this is a related rates time, and it's the rate of change in respect to time. So I'm going to take the derivative of both sides in respect to time, okay? So, oh, wait, but before I do that, there's a fact that I know that is constant and is not changing. Yikes, my eraser, please come. Whoa, good grief, go back to pen mode, give me an eraser. Please, eraser, why won't you come? How about if I just undo? Oh boy. Eraser. How come I won't erase? Oh, good grief. Okay, then let's just block it off then. On the AP exam also you can do that. So before I start, I'm sorry you guys, volume equals going to be pi. Now the radius is constant in this problem. The can is 10 square, radius of 10. So then we know volume is 100 pi times h. Now I'm going to take the derivative of volume in respect to time. Okay? Now here, the only variable is h. So it's going to be 100 pi, and it's the derivative of h in respect to time. Okay? So now we want to find out at 7, what is the rate changing? Well, dh dt, we know that to be our function s prime. So then we can rewrite it. So it's 100 pi times s of prime at 7. Now use your calculator and find the value at 7 for the derivative function and multiply it by 100 pi. and then you should get approximately 602.218. Now this is the rate of change of volume. What is volume always measured in? Units, units squared, units cubed. It's units cubed. So it's millimeters cubed per day is the rate at which the volume is changing. Now let's go into part D, okay? And so for part D, we are said during the same 60-day period, rain on a different mountain, Mount Masoon. Woohoo! Okay, so for this then, it's accumulating, but we have a new function now. And this function is m of t, and that represents the height, okay? So then we are told that we need to look at the difference between these two rates. So it'd be m prime minus s prime t, and use the intermediate value theorem to show that there will exist a time between 0 and 60. Okay, so in other words, I'm going to go to a new page. I'm going to need to calculate these values of m of 0 and m of 60. Okay, so I need to find out, well, what is the height at the rate of change of height at time 0, and what's the change rate of height of time 0 for s. So then I use this and I put it into the derivative function for m, and I would get 0.825. And then I use my calculator and I put the 0 into the s prime function, and I'd get 1.5. So then we know then the rate of change of the differences would be a negative 0.75. Okay, now let's look at how the rate of change is occurring at 60. And at 60, when we substitute that into the function, I would get 72.825. And then when I replace that into the function for s, I would get 3.447. Now when I subtract those, then the difference is 69.337. So then the question was, we had to say that there will exist of d of t, which is equal to 0. Then according to the intermediate value theorem, since I have a value of ranges from negative 0.675 to 69.337, then we are guaranteed that the value 0 will exist because this is a continuous function. There you go. That is the solution to problem 1. This is an explanation to problem number 2 of the practice test number 2. Okay, so in this problem, we are beginning with a 12,000 liter tank and it's filled to capacity. Okay, so at time 0, so we know that at 0, the tank level is 12,000. And water begins to drain at a rate modeled by R of t. So this is the rate at which the water is draining in liters per hour. Okay, liters per hour. Okay, and it's a piecewise function. We can see it's going from 0 to 5 and then greater than 5. So the first question is R continuous? Well, in order for a function to be continuous, the first criteria is that f of 5, or I should say that R of 5 exists. Well, does it exist? Yes, we can substitute the number 5 into the first part of the piecewise function, and we would get a value. Okay, now let's go to the second condition of continuity. The second condition says that as I approach the function R of t, as I approach 5, that the limit will exist. Well, since it's a piecewise, we have to approach it from the left and the right. Okay, so as I approach then the time from the left, okay, so we can substitute in 5 into the function. So we would place 600 times 5 over 5 plus 3, and that value would be 375 at R of 5. Now if I look at the limit as I approach 5 from the right, then I would substitute 5 into the function 1000 e to the negative 0.2 times 5. And that value would give us 367.879. Remember, 3 decimal places. Now we notice that these two values are not equal. So since the limit from the left of 5 does not equal the limit from the right of 5, I kind of wrote it and said it differently, then the function is not continuous. Okay, now let's go on to part B. So in part B then, we are asked to look at the average rate of change, okay? Well, since we are given the velocity function, we just need to find the average value of this function. So we know that to be from 0 to 8 of R of t, and then we're going to divide it by the interval 8, or I can write 1/8. Now this is unique in that I have to split it up into two integrals because we have two pieces of the function. So we would go from 0 to 5 of 600t over t plus 3 dt, and then we would add that to the integral of 5 to 8 of the new function, which is 1000 e to the negative 0.2 t dt. Okay, and I would use my calculator to get that answer, and then that would be 258.052 or 053. But remember, 3 decimal places. Okay, now let's go ahead and look at the next part. So C says find r prime of 3. Well, interesting, r prime of 3, since r is already a rate of change, we're going to find the derivative of rate. So really we're looking at it, how is the rate draining out of the tank increasing, or is the rate at which the water is draining out decreasing? Notice it's not acceleration because it's not a position velocity problem. So check your work on that. So r prime at 3 then, so we are going to look at when time is equal to 3. So then we would be taking we would be looking at the function 600t over t plus 3. Okay, so in your calculator, you're going to find the derivative of this. So the derivative of this function at t equals 3. And so when you do that, you should get the number 50. Now, how do you explain that using correct units? Well, you would say, since it's a positive number, the rate is increasing, right? So the rate at which the water is draining, from the tank. Now remember, it's important to write these sentences. From the tank, now remember, use units, at t equals 3 hours, okay, is increasing, so the rate is increasing. And what is that rate that it's increasing at? At 50 liters. Now since it's the second derivative, it's going to be per hour squared. There you go. That's how that would be done properly, okay? Make sure you use proper, in the situation, you got to use the units and state it correctly. Okay? Now, part D, write, but do not solve an equation, get that equation, involving an integral to find the time A when the amount in the tank is 9,000. Well, I know to find the amount in the tank, I would take the integral, the integral of the rate of change. Okay, now what are my limits? Well, I want to go from 0 to some time A when I have a value of 9,000. So that means when I take the integral, then I'm going to have, the amount at a certain time A minus the amount at 0. Well, we know that to be the amount at certain time A, we want that to be 9,000, and we know the initial value is 12,000, okay? So then we have the integral from 0 to A of my rate of change will be equal to negative 3,000. Or I can say take the opposite of the amount of water that has drained out, okay? And that would be equal to 3,000. There you go. That's it for problem 2. Well, this is the solution for number 3 of our practice test. So in this problem, you can see that we're given the graphical approach, and we're given two functions, f and g. So f is the square root of x, and g of x is 6 minus x. I'm going to go ahead and label my diagram just so that I can remember that clearly. And R is the region bounded by f and g. So part A, find the area of region R. Okay, so area is, between the curve and the x-axis. And I notice for this, I've got two parts clearly here. So my first part goes from 0 to 4 of f of x. And then I have to find the area of the curve from 4 to 6 of g of x. Okay, now let's start taking this apart. So f of x, we are told, is the function the square root of x. And g of x is the function 6 minus x. Now you could have done this two different ways for the 6 minus x, because notice it's a triangle, so the area under the curve is 1/2 base times height, And the height is 4, the base is 2, so 4 times 2 is 8. And then times half of that would be 4. Am I doing, wait, no. The base is 2, the height is 4,